Routing a maximum number of disks through a scene of moving obstacles. Jeondong Kim, Joseph Mitchell, Valentin Polishchuk, and Arto Vihavainen. World air traffic volume has been increasing at an average rate of 4.6% per year. An algorithmic challenge in accommodating the safe routing of this increased traffic flow is the task of planning multiple safe paths for aircraft amidst moving weather systems. Control of en route flights is partitioned among sectors of airspace. Flights with significantly different headings are kept altitude separated. Thus, on one flight level of a sector or other region of airspace, the routing of multiple flows of safely separated aircraft gives rise to a two-dimensional problem which we formally capture as follows. We are given a polygonal domain consisting of an outer bounding polygon with polygonal holes that serve as constraints where travel is forbidden. The holes, which may model, for example, weather hazards, move slowly along known trajectories that are given by forecasts. Two edges of the outer polygon are designated as the source and the sink. The goal is to find maximum number of trajectories for unit disks entering the domain through the source and exiting through the sink. It is required that during the motion the disks do not intersect each other and the obstacles. In the XYT space, every hole, when moving, sweeps a three-dimensional obstacle. Each disk sweeps a slanted and curved cylindrical tube. The tubes do not intersect each other and the obstacles. Consider a small part of a feasible tube. Since obstacles move slowly, no obstacle penetrates the right circular cylinder contained in the part. Each feasible tube contains a stack of such cylinders. Inside the stack there exists a chain of oblique cylinders. Such a chain exists, of course, inside every tube. We show how to find the chains by discretizing the time and space. Slice the time into equal length intervals. At every slice, we pack a maximal number of disks of radius 1/3. Next, we build the motion graph, whose nodes are disks in the packings. Edges of the motion graph connect each disk to all disks at the next time slice that the disk can possibly reach by a straight line obstacle-free motion. We connect the disks along the source and the sink to a supersource and a supersink nodes. The main step of our algorithm is finding the maximum number of disjoint supersource-supersink paths in the motion graph. Each such path corresponds to a tube of radius 1/3. By construction, every tube is obstacle-free and thus defines a feasible path for a disk. Unfortunately, our construction does not prevent the tubes from intersecting each other. To resolve the intersections, we decrease the radius of the tubes and slightly bend them. This way, we obtain a set of disjoint tubes. Overall, our algorithm produces just as many routes as can be routed optimally for unit disks moving with maximum speed 1. It does so by compromising on the radius of the disks as well as the maximum speed of motion. We allow the user to choose the time discretization step delta t. With a finer discretization, one can route disks of larger radius. It comes though at the expense of increasing the maximum speed of the disk's motion.